Okay, so today we're gonna do just one more example on 3.5. I hope you guys started looking at the homework from WebWork. Hopefully that explains how to do examples for non-homogeneous case. So let me go ahead and start giving you the topics for our next quiz, and then we'll start with an example from 3.5. So for next week, we're going to have a quiz number 3. So we're going to have quiz number 3 Tuesday, June 30th at 7:40 p.m. So that's gonna be 20 minutes long, or so it depends how much time it takes me to finish the quiz, and then I'll expand the time for you guys. So maybe 30 minutes. I'm not sure how long that will take, but just make sure you're available for at least 30 minutes for next quiz, because it's after class, so you'll probably run up to 8:10 or 8:15ish. Just make sure you have that time slot available for next Tuesday, okay? So letting you know in advance. And then the sections that you are required for this quiz are 3.5, 3.6, and let's put a question mark with 3.7 and 3.8. So I'll clarify that at the end of today's lecture. So if we do get to 3.7, that will be on the quiz. If we don't, then it's not going to be on the quiz. So that's why that question mark is there. Okay? All right, so any questions? Any questions before I start? Okay. Okay, so let's go ahead and start with this example. So I typed a question for us to work on. I think we can do this one. So this is from 3.5. So we're still continuing with 3.5. So for this particular question, we want to determine the form of the particular solution yt, or you can use y sub p, of the non-homogeneous differential equation. And we do not want to determine the coefficient, because once you have the correct form, determining the value of the coefficient is just simply going through the algebraic work very carefully. Okay, so I'll leave that up to you to finish, but let's see if we can go ahead and find solution to this problem. So to use the method of undetermined coefficient, as we talked about last time, we first determine the solution to the corresponding homogeneous equation. So let's find YH. So we write out the homogeneous equation to this. We have y double prime minus 6y prime plus 9y equals to 0. And then we write out its characteristic polynomial. That will be r squared minus 6r plus 9 equals to 0. And this can be factored into x minus 3, well, not x, right? R minus 3 square equals to 0. So we have repeated roots. We have r1 is exactly equal to r2, which happens to be 3. So the homogeneous solution, it's going to be c1 e to the 3t plus c2t e to the 2t. Okay, so that's the solution to the 3t homogeneous part. Now let's go ahead and determine. So this is the part where you are going to use the undetermined coefficient method, and we want to determine what is the form of yp, or in this question I use the notation y big Y of t. So we can just write that. Okay, so let's see. Well, you see how we have a function here and we have another function here. So you want to think of, you have different pieces, different family of function that equals to your g of t, right? So we're going to need particular solution for each pieces. So let me just rewrite the second part. So we need 1 for 5t squared. So I'm going to call that to be yp1. So that will be one particular solution, right? Corresponding to that. And then minus, and for the next one, I see that they both share e to the 3t, so I'm going to factor out e to the 3t. So we have 4t plus 2 times e to the 3t. So this will need another particular solution. So we'll call that yp2. Okay, so the reason I'm doing this is because I have more than one function that represents g of t. Whereas for last class, we only had one function that described g of t, or product of two functions, or 3 describes g of t, but here you have a sum or difference of different functions. So you need different particular function for different family of functions. I hope that makes sense. So yp is going to be yp1 plus yp2, meaning the particular form for the first one and the second one. So let's determine what is the first one. What is yp1? Well, yp1 is, what is yp1? What kind of equation is that? What kind of function is that? Anyone? Right, so it's a polynomial of what degree? 2, right? So a standard way of writing a polynomial of second degree will be at squared plus bt plus c. That's a polynomial of degree 2, right? So now, okay, we determine the form for the first one. Now, does any of these terms overlap with my homogeneous solution? So I'm looking at this piece right here. It doesn't, so we don't need to modify it. So we found our yp1. Now what about the second one, yp2? So let's determine what's the family of function for yp2. So yp2 involves product of two types of functions. Right, and so for the polynomial part, we need a first degree polynomial. So the first degree polynomial will be, so let's say dt plus e, because I already used up a, b, and c. So that's the first degree polynomial, and the exponential is just e to the 3t. So that's a possible form for yp2. Now I want to check, does any of these overlap with my homogeneous solution? So you can, Right, so this one will overlap. And then what about if I distribute it to this one? Will that overlap? Yeah, so that means they both overlap. So what will be the t power that I can multiply it by so that it doesn't overlap at all? Okay, second. So let's check. If I did t to the 1 power, then the first term is okay, but then the second term will be in trouble because you're going to have e to the 3t, but that's going to overlap with the homogeneous part. So that means if I do t squared, then none of them are going to overlap. So this would be the form for the particular solution of yp2. Okay, So altogether, our form for the particular solution, y of t, is going to be at squared plus bt plus c plus dt cubed e to the 3t plus e t squared e to the 3t. So that will be the form of the particular solution. And then from here you can start differentiating, taking its first and second derivative to determine the coefficients. But in this question, I'm not going to do that because I think that's just algebraic skills that you need to brush up on. So you can take care of that part. Okay. So any questions on this? All right, so if there are no questions, let's move on to the next method that we want to talk about for non-homogeneous equation. So the next section we have is 3.6. So in 3.6, we're going to learn the method of variation of parameters. So this is more general method for non-homogeneous case, because we saw yesterday that for, so if I go back to my notes from last class, so here's the remark. When do we use this method? We use this method if we have g of t happen to be an exponential, if it's a polynomial, or if it's sine or cosine. Then you can use the method of undetermined coefficient. But what if g of t happens to be some other function? So that means you need another method to compute its solution. So that's why we have this method, which is more general method. So this method will apply to any g of t. So let's call this general method to solve non-homogeneous. Okay. So you should know both methods because and the question might ask you use this method to do it. So why not know both of them, right? And sometimes one method is easier than the other, so that's why we have both. So if we start with the following differential equations, ay double prime plus b y prime plus cy equals to some function g of t, and assuming g of t is not 0, because if it's 0 then there's no use to use this method. So we know the solution to the homogeneous case, right? So we so far know the solution to the homogeneous. So we know ay double prime plus by prime plus cy equals to 0 has a solution, and we know those solutions are we call them y1 of t and y2 of t. So these two will correspond to the homogeneous solution. So we say that y sub h is equal to c1 y1 of t plus c2 y2 of t. Right? So the linear combination of y1 and y2 will form the solution to the homogeneous of this equation. Well, now here's the thing. We want to vary the parameters. And here our parameters are c1 and c2, these constants. So here's the note. c1 and c2 are parameters. Okay, so the idea behind this method is to vary the parameters. So we're going to assume that c1, so the idea of making them as parameters, we want to vary them. So you want to make them a function of t. So instead of just calling them constants, we let them be some function of t. So we're going to introduce two new functions to replace C1 and C2. So we're going to assume the general solution is y equals, so I'm going to replace C1 with u sub t, so it's a function of t, times y1 of t, plus now C2 I'm going to vary it with v of t times y2 of t. So all I did was replace my constants with v and u, and they're now functions, okay? So just to write this in a simpler notation, I'm just going to say y is equal to u times y1 plus v times y2. So that's the starting point. We're going to assume that the solution takes this form. Now the big question is, what are these unknown functions? What is u and what is v? That's the goal. So I'm going to show you the derivation to get the formula for u and v. But again, you don't have to know the derivation for a test, but you should understand where things are coming from. Okay, so let's derive them first, and then I'll box the formulas for you. So if this is the general solution to this differential equation that we're solving right here, this non-homogeneous, that means I can take its first derivative, second derivative, and plug it in, right? So let's do that. So the usual drill, we compute y prime and y double prime. So then we have the following. So because u and v are functions, we will end up using product rule to compute their derivatives. So y prime, it's going to be u prime times y1 plus u times y1 prime plus v prime times y2 plus v times y2 prime. So just using simple product rule, we have y prime. Well, now I'm going to impose a condition to this so that it works out nice. Okay, so there's always reason why we do the things, because they just work out well. So we're going to impose the following condition. Okay, so let's rearrange them. So I'm going to say, okay, let me just rearrange these. So I have u y1 prime plus v y2 prime plus, and then we have u prime y1 plus v prime y2. So the condition I'm going to impose is that I'm going to let this go to 0. Okay, so just trust me on this, it will work. So we're gonna let that piece go to 0, so that means y prime is just u y1 prime plus v y2 prime. That will be y prime. Now let's compute its second derivative. So this is the first condition. Okay, we're going to impose another condition at the end. So now let's compute y double prime. So y double prime, again using product rule, we have u prime y1 prime plus u times y1 double prime plus, now for the second term we have v prime y2 prime plus v y2 double prime. Okay, so this is the expression that will represent y double prime. So we have an expression for y prime, that's this piece, and y double prime is going to be this piece right here. So let me know if you guys have any questions. Now, so we have our derivatives. We're going to plug them into this equation right here that we're starting with. So let's plug everything into this equation. So let me call this star. Okay. So let's plug into star. So plug in y prime, y double prime, and y, right? Because we need that too, into star. So we get the following. We have a times y double prime, so that would be u prime y1 prime plus u times y1 double prime plus v prime y2 prime plus v y2 double prime plus, and then we have b times y prime plus c times y. So we have b times y prime, well, y prime is this expression we have, u times y1 prime plus v times y2 prime plus c times y. Well, y is u times y1 plus v times y2. That's the general assumption we made from the beginning. Okay, so all of it equal to g of t. Okay, all right. So now let's clear things up. So again, I'm going to rearrange the term, and let's see what it looks like. So now let's group them in the following way. So we have, so I'm going to group them this way. I'm going to group a times u prime y1 prime plus v prime y2 prime into one parenthesis, and then I'm going to rewrite the rest in the following way. So I'm going to rewrite, so I already used up which ones? I used up this one and I used up this one. And remaining terms, I'm going to rearrange them with all the terms with y1 and all the terms with y2 and their derivatives. Okay, so that's the next thing I'm going to write down. So I have a times u times y1 double prime, and then the next one that involves y1 is b times u times y1 prime plus c times u times y1 plus, and now I'm going to rewrite the terms involving y2. So I have rewritten this one, and this one, and then I'm going to rewrite the rest. So we have a times v y2 double prime plus b times v y2 prime, and the last term I have is c times v y2 is equal to g of t. Okay, so let me know if you guys have any questions so far. Okay, well, now I'm just gonna again rearrange them a little bit more. So again, I still have a times u prime y1 prime plus v times y2 prime plus, now from the next three terms I'm going to pull out the u. So we have a y1 double prime plus b y1 prime plus c y1 plus, now for the second, so the next last three terms we're going to factor out the v, and we're left with a y2 double prime plus b y2 prime plus c y2 equals to g of t. Well, now we should be able to make some conclusion. What is this equal to? What did we assume? We said that we know the solution to the homogeneous case, right? So that means, isn't y1 solution to the homogeneous case? Are you guys following me? So here we said that, so where are we? Right here. So we have the non-homogeneous equation, right? And then we said we know the solution to the homogeneous case. So that means y1 and y2 solves the homogeneous, right? So here, after I combine like terms, I have y1 double prime plus y1 prime plus y1. That's one of the solution to the homogeneous part. Do you agree? Right? So this is 0 because it solves the homogeneous case. Now, what about this one? Right, because y2 also solves the homogeneous case. So these are all both 0. So the only thing we're left to impose is that the remaining piece is equal to g of t. So we're almost there. So we have a times u prime y1 prime plus v times b prime y2 prime is equal to g of t. Or you can just call it g. Okay, so that's the second condition we have. So this will be the second condition. So from beginning, we started with this condition 1, u prime y1 plus v prime y2 is 0. So we have the following. So this is nice. So we impose the following conditions. So one we had was u prime hold on, let me just double check. Right, so u prime y1 plus v prime y2 is 0. So we have u prime y1 plus v prime y2 is 0. That's one. And the second one that's right above here, we have a times u prime y1 prime plus v prime, so a goes with both of these, is equal to g of t. Let's call it g. So what do we have? We have a system of equation. Now from here, the idea is to solve the system of equation. How are we going to solve it? Well, we're going to be using Cramer's rule to solve this. Now, so let me know if you guys have any questions up to this point. Are we good so far? Okay. So our goal is to, so what is our goal? Is to solve for u and v from here. But we don't have u and v yet. We have u prime and v prime. But once you know an expression for u prime, all you have to do is integrate to get v or u, right? So that's where we're heading. So think of it as, so you should be thinking this way. You should be thinking you have a system of equation. Let's say a1x plus b1y equals to some constant, and then a2x plus b2y equals to another constant. So you want to use Cramer's rule to solve this system, and think of it in those terms by using these variables that we have, which is u and y1 and y2 and v. So in order for us to solve the system, we have to know the determinant of the system, right? So to find the determinant, well, it's going to be the matrix that we're going to set up, and that's going to be the Wronskian. So we have the Wronskian is y1 a times y1 prime y2 prime. So that's the determinant of the system, which is the Wronskian in our case, right? So what is this equal to? So I'm missing an a. So this is going to be a times y1 y2 prime plus y1 prime y2 times a. So I'm just going to factor out the a. So that's the Wronskian. Well, now by Cramer's rule, we can find v prime or u prime. Greg, do you have a question? Oh, it's subtraction. Thank you. Good catch. It's always subtraction. Yep. Thank you. All right. So we have the Wronskian of the system, but now if I want to solve for u prime, so I'm looking at the first column, that means I'm going to be replacing these coefficients with 0 and g. So I have the following matrix. So if I want to solve for u prime, we have this new matrix. So the first column will be replaced with those constants, 0 and g, and the next column will remain unchanged, a times y2 prime, and then all over the determinant of the system, which is the Wronskian, right? Well, a times the Wronskian. So that would be u prime. But what is this equal to? This is equal to, so the 0 times a times y2 will go to 0. So let's check if there are any question. Zero over g. So it's not 0 over g, it's 0 and g. These are the entries. 0 and g is the entries for the column replacing y1 and a times y1 prime. Okay? So this would be equal to negative g times y2 over the Wronskian, right? So that would be the expression for u prime. Well, now, sorry, this is a times the Wronskian. Well, now how do we solve for u from here? We have u prime is equal to an expression. How do we get u? We integrate. So u would equal to the integral of negative g times y2 over a times the Wronskian respect to t. Now, keep in mind that for all these questions that you're going to be working on, this a right here is going to be always 1. So you can modify this formula. So if I were to modify this, you can write u is equal to negative integral of g times y2 over the Wronskian dt. So that would be a specific, but in general it will be a times the Wronskian. So that's the formula you have to remember. This is how you're going to be solving for u, the function u. Now similarly, we can solve for v. The same idea. We replace the second column of the Wronskian with the constants 0 and g, and then just set it up using Cramer's rule. So similarly, we have v prime is equal to this matrix. So we keep the first column, that will be y1 and a times y1 prime. Now second column will be replaced with 0 and g, and on the bottom we have the determinant of the system, which is a times the Wronskian. Again, you can replace a with 1 because most of the cases will be 1, except maybe some homework question you're going to have a is not equal to 1. So if I were to finish writing out this formula, we have y1 g times y1 over the Wronskian times a. So that will be the expression for v prime. So again, if you want to get v, we integrate both sides. So v is equal to the integral of g times y1 a times the Wronskian dt. Again, if a is 1, we have v is equal to the integral of g times y1 over the Wronskian. So that's probably the formula you'll see in the textbook. Okay, so these are the ones you have to remember. Again, the derivation is just to show you where things are coming from, but if you're not a math major, you probably don't need to know them, but if you are, you should enjoy them. Okay, so these are the two magical formulas for u and v. So once you know these integrals, once you have them out, you just write out the general solution, which I boxed right here, will be u times y1 plus v times y2. That will be the general solution. So any questions on these formulas? So this one you must remember. And this one you must remember. Okay? Alright, so how do you guys like the derivation? Is it okay? Okay, alright, that's good. Right, every time you see a derivation for the first time, it's always confusing. But just go through the details maybe later, or if you come to my office hours, maybe I can do it again, and then hopefully it'll make sense. Alright, so from here we know the general solution is y equals u times y1 plus v times y2. So I also want to mention, when you're working on web work for this section, they might use different notations for these function u and v. Just make sure you match it up with our notation so you don't get confused where the things are coming from. But the idea is the same, okay? It could be using different notation, but the formula still holds. Just replace them with the variable they have. Okay, so now let me give you the steps for using variations of parameters method. So here are the steps. So the first step is always find the homogeneous solution. Always. Even for undetermined coefficients method, you still have to know what are the homogeneous solutions. Once you have your homogeneous solution, then you want to compute the Wronskian. The Wronskian of y1 and y2. So here's something I also want to mention. Identify, I would say label. Label which one is y1, which one is y2. You want to pick your solution, y1 and y2, and then compute the Wronskian of the two solutions. After you have computed the Wronskian, well, you find what is u and what is v. And then once you have successfully finished integrating, you state your final general solution. You have y equals u times y1 plus v times y2. And from here you can pick up which one is the homogeneous solution, which one is the particular solution. Okay? So let's illustrate this method using an example. So we always understand mathematics better when we do an example. So let's do that. So here is our first example for this section. Let's find the general solution of y double prime plus 4y equals to 8 tangent of t between negative pi over 2 less than t less than pi over 2. Okay, so here's an example where you are forced to use variation of parameters. Why do I say you are forced to use this method? Can someone guess why are we forced to use this method, not undetermined coefficients? Right, because of g of t, right? G of t is tangent. Now, do we have a formula for g of t here that happens to be tangent? No, so that means there's no way we can determine the form of the particular solution using undetermined coefficients. So we're forced to use this method. And it's kind of nice. You will see how everything really fits in. So we're going to use this method to first thing compute the homogeneous solution. So let's go ahead and do that. So we write out its corresponding homogeneous equation. So let's find YH. So we have y double prime plus 4y equals to 0. So our characteristic equation is r squared plus 4 equals to 0. So what is r? R is plus and minus 2i, complex. So we know how that solution looks like. So YH is going to be C1 cosine of 2t plus C2 sine of 2t. So we have the solution to the homogeneous part. Now the second step is to compute the Wronskian, but before that you want to identify which one you're calling y1, which one you're calling y2. So what I would do, I'm just going to go the way I have written. I'll call this one to be y1 and this one to be y2. You can switch them around, it's up to you however you label them. Okay, so now that I have labeled the functions y1 and y2, let's go ahead and compute the Wronskian. So the Wronskian of y1 and y2 is equal to this matrix. So y1, that's cosine of 2t, y2 sine of 2t. And the second row we're going to put their derivatives. So we have negative 2 sine of 2t, and then derivative of sine 2t is 2 cosine of 2t. So that's the setup for the matrix. Now let's multiply them. So we get 2 cosine square of 2t plus, because I have a minus and the minus from the matrix, 2 sine square of 2t. Now you guys should know what this is equal to. This is an identity. Right, right, so this is just 2. Okay, so we have the Wronskian, so step 2 is completed. Now step 3 is the part that requires more work, where you actually do the integration because u and v are formulas that involves integration. So let's do that. So now we compute u. U happens to be, what's the formula for u that we just derived? So u is negative g times y2 over the Wronskian, a times the Wronskian, but if you notice, a is 1, right? So a is this coefficient right here. It's always going to be a 1, so we can just say a times the Wronskian. So we have the integral of g times y2 negative over the Wronskian dt. So this would be negative g of t. Well, what is g of t? G of t is 8 tangent of t, so that's 8 times tangent of t. Y2, well, I picked y2 to be sine of 2t, so that's where I'm going to replace here, all over the Wronskian, which we just computed as 2 dt. So now the difficulty comes in, how well do you know your integration? So this is when Calc 2 comes in again. Integrate. How do we integrate this, guys? Give me some ideas. Uh-huh. Okay, so let's do that, right? Let's come up with some ideas. So you just play around with this and see which way works. I can do 8 over 2, that's -4. And then, so tangent, so who suggested that? Let's check. Sadia. Okay, thank you. Alright, so Sadia says, let's rewrite tangent. I like that. Let's rewrite tangent. Well, it doesn't help, right? Because their arguments are different. Sine 2t and then sine t over cosine t. How do you rewrite sine 2t? So let's recall, right? This is something from, again, pre-calculus. That's an identity for sine 2t. So Gabrielle says it's 2 sine t cosine t. Perfect. So sine 2t is 2 sine t times cosine t. Alright, so we have the recall and we're going to apply the recall here to sine t cosine t. And then maybe now we can kind of play around with this and integrate. So I can do some cancellation. So cosine cancels out, and then we are left with something really nice. So we have the following, and the 2 and the 4 I can multiply them. We have the integral of sine square of t dt. Oh boy, how do you integrate sine square of t? So 1/2, 1 minus cosine of 2t. Right? So this should be the identity you're recalling. Right? So, okay, do you guys follow? So this is again coming from algebra or pre-calculus, identities from pre-calculus maybe. So I'm going to apply that identity for the integration so that we can integrate. So we have the following now. So we have -8 over 2 times the integral of 1 minus cosine of 2t dt. Now that we can integrate piece by piece. So this is equal to what? -4 integral of 1 respect to t, that's t, minus integral of cosine 2t is going to be sine 2t over 2 plus a constant c. I'm going to put c1 because we're solving a second order, so we should have two constants, c1 and c2. So that's the solution or the solving expression we have for EU. Now let's simplify this. It looks not so pretty yet. So U is equal to -4t minus plus 2 sine of 2t plus c1. So that will be the expression for U. Any questions on this? Does anyone have a question? Alright, so someone has their audio on. Can you mute your audio? Okay, so alright, so let's go back and find V now. So we found U, now let's compute V. Well, any questions for U? It took us a while, but we got it. So we had a lot of flashback, right, on identities and then integration techniques. So some things to keep remind ourselves of. Now what is V? Well, V is the integral of g times y1 over the Wronskian dt. that's the formula we arrived for v. So now let's plug these in. So g is 8 tangent of t. What's y1? So y1, I labeled it to be cosine of 2t. So cosine of 2t over the Wronskian, that's 2 dt. And now we go through the same process of solving this integral. So any ideas on how do we proceed? What do you guys think? How do we integrate this? So I'm going to go ahead and rewrite tangent. Right? Can you guys hear me? Okay. Yeah. Right. So that's what we're going to use. So yeah, thank you. So we rewrite tangent as sine t over cosine t, and then cosine 2t. So let's go back to recall and just add it on our list. So cosine of 2t also we know as some identities. So there's 3 ways you can rewrite the double angle of cosine 2t. So one of them is cosine squared t minus sine squared t. And there's 2 more. Another one is 2 cosine squared t minus 1. And then there is 1 more. So you can figure that out. So I'm going to use the second version because you will see why it works. Okay. So I'm going to replace it with 2 cosine squared t minus 1. So this is 2 cosine squared t minus 1 dt. Okay, so now let's simplify this. So we have the following. We have 4 outside the integration. So we have sine t over cosine t times 2 cosine squared t minus sine t over cosine t times 1 dt. So all I did was I distributed the tangent, sine over cosine. And now I can integrate this because it looks much more simpler than before. So I can cancel out one of these and then I can rewrite. So we have the following. We have 4 integral of, well, times 2. So times 2 sine t times cosine t minus, and then 4 times the integral. Sine over cosine, I'm just going to rewrite it as a tangent because we know how to integrate that term, dt. So I separate it into 2 separate integrals, and now I can integrate this. How do we integrate the first one? Yeah, that will do. So we can use the u substitution. U is equal to sine, and then its derivative of cosine. So that works. So we have 4 times 2, that's 8. So sine squared t over 2 minus 4. Now, what is the integral of tangent? Do you guys remember that? So let's recall. What is the integral of tangent of t dt? So that's something you should never forget. This is ln of secant t plus c. So that's an integral you always remember somehow. So you could remember as negative ln cosine t, that's also correct, or ln of secant t. They're exactly the same. Okay, so that's what I'm going to rewrite here for the last integral we're integrating. 4 ln of secant of t plus a constant c2. Okay, so now conclude v is equal to, I'm going to simplify this, 4 sine square of t minus 4 ln of secant of t plus c2. So that's the expression we have for v. So we're almost to our general solution. Okay, so what is the general solution we assumed? We assumed that the general solution is going to be y equals u times y1 plus v times y2. That was the general solution. Now let's plug in these pieces. So y is equal to u. U is right here. So let me see if I can copy and paste. So that way I don't have to rewrite. So this is u. Let's plug it in here. So we have, oh, so it looks like, oh, so I'm having difficulties with my solution. Right, we did all the hard part, but now just copying and pasting it doesn't work. Alright, it doesn't work. Okay. Okay, so I'm just gonna copy it here. Yeah, it doesn't allow me to pull it. I don't know why. Okay, whatever. So u, that's this function right here, negative 4t plus 2 sine of t plus c1 times y1. So what is y1? Let's go back again. Y1 is, where's y1? Right here, cosine of 2t. So we have y1 cosine of 2t. And I'm going to go ahead and erase this part because I don't need this. And then the second part is v. V is this expression we just found, for sine squared t minus 4 ln of secant of t plus c2 times y2. y2 was sine of 2t. So that one I remember. And there you go, you have your solution. Now from here you can pick up your homogeneous solution and your particular solution. So just let's write it in that form. So we have y equals, I'm going to go ahead and distribute these functions. So we have c1 cosine of 2t from the first parenthesis. From the last parenthesis I'm going to pick up c2 sine of 2t and just rewrite the rest. Plus we have negative 4t cosine of 2t plus 2 sine t cosine of 2t, and then from the next parenthesis, if I distribute our sine 2t, we have 4 sine square of t and sine of 2t minus 4 ln of secant t times sine of 2t. Can I combine any of these functions? Not really, right? So I will just leave it right here. Yeah. Alright, so there you go. You have the method of variation of parameters. Any questions on this method? So from here, can you pick up which one is the homogeneous, which one is the particular solution? So where is the homogeneous? Right, so this portion right here, this is the homogeneous we initially found. So that means the remaining piece is the particular solution, okay? So the remaining ones are YP. And you see how the coefficients are already solved. Whereas on determined coefficient, you kind of have to go through the algebraic work to solve for those unknown coefficients. So this method is nice, but it takes you a while because sometimes these integration can be very difficult. So that's why you have to have more than one method to compute solutions. All right, so how fun was this method? Oh, Tris, he's banned from this section. I'm not sure why. Okay. I'm not sure why he's banned from the section, but he should still be able to come in. Okay, so yeah, I don't know how to fix this. I think something happened to Blackboard and it probably kicked him out. But okay, let's carry on. I can't lose our class time. All right, so any questions on this method? All right, which method do you guys prefer? So I'm gonna do another example, and then we'll probably start with 3.7. Okay, so Sadia says she likes the other method better. That's good. Okay. All right, and the rest of you, I don't know, no opinion. That's okay. All right, so example 2, let's solve the following. So let's solve, so let's do y double prime plus 4y prime plus 4y is equal to t to the negative 2 times e to the negative 2t. And assume that t is greater than 0. Okay? So let's see if we can compute the general solution to this differential equation. So let's use the variation of parameters. Now, this is another case where you are forced to use variation of parameters. Why? So, Driss, you're back. What happened? Oh, really? Oh, yeah, I don't know what happened. I'm just looking through my list and a weird thing happened. So, but I'm glad you're back. Yeah, that's okay. But I'm glad you're back. So, join us. So we're doing another example for this method of variation of parameters. Now here, your g of t is, again, it's not a polynomial. It has exponential, but it also has a non-polynomial portion to it. So you can't really consider it as polynomial times exponential. That doesn't fall into. And it's not a sine or cosine. So we're going to use variation of parameters. So first thing, again, we want to compute the solution to the homogeneous equation. So let's find YH. So we have y double prime plus 4, y prime plus 4 equals y equals to 0. So we have the characteristic of this, r squared plus 4r plus 4 equals to 0. And we can factor this, we get r plus 2 square equals to 0. So r1 is equal to r2, which is negative 2. So we have real repeated roots. So the solution to the homogeneous equation is going to be c1 e to the negative 2t plus c2t e to the negative 2t. Okay, and from here you're going to identify which one is y1 and y2. So I'm going to go ahead and label the first one y1, second one y2. So let's label this one y1 and let's label that one y2. Once we have labeled y1 and y2, we're going to go ahead and compute the Wronskian. So let's go ahead and do that. So it looks like I can't draw lines for some reason, but okay, good enough. So the Wronskian of y1 and y2 is equal to the matrix. Shuman, do you have a question? Because of t to the negative 2, that's not a polynomial. Right? So polynomials are of the form, right? Pn is equal to an t to the n power, right? Or n is greater than or equal to 0. Yeah. Okay. So let's go back to the Wronskian. So we have the Wronskian would be y1, which is e to the negative 2t, and y2, that's t e to the negative 2t. And then their derivatives on the second row, negative 2e to the negative 2t. And the next one you have to use product rule, so this is going to be a bit more work, but we can do it, right? Never give up. So we have e to the negative 2t minus 2t e to the negative 2t. So someone just double check my work. I could be missing a negative sign somewhere, maybe. It looks right. Okay. I think it looks right. So, okay, now let's multiply these entries. So we have, what do we have? E to the negative 4t minus 2t e to the negative 4t. And then from the other entries we have plus 2t e to the negative 4t. And if I simplify this, this would just simply be e to the negative 4t. So that would be the Wronskian. Okay. Alright, so we computed the homogeneous solution, we computed the Wronskian. Now we compute what is u and what is v. Okay, let me know if you guys have any questions. So now let's compute u. U is equal to negative g times y1 over 8 times the Wronskian. Again, a is 1. A is this coefficient right here in front of y double prime. That's 1. So it's over the Wronskian dt. So we have the integral of negative g of t. G of t is t to the negative 2 times e to the negative 2t. T to the negative 2 e to the negative 2t over the Wronskian, that's e to the negative 4t dt. Okay, so this is not so bad. It looks nice. What do we get? Let's simplify. Negative integral of, go ahead. Yeah. Sorry. Oh boy. Thank you. Good catch. So I have to fix this piece right here, and I have to rewrite this one. Thank you. Appreciate it. Y2. Which one did we label Y2? That's t e to the negative 2t. Okay. Whew. Alright, so we have t to the negative 1, and then e to the, let's simplify those terms. So we get e to the 2t. So this would simplify to e to the 2t. Okay, someone double check my work. I think it looks right. So how do we integrate this? So I'm going to rewrite this one more time. Negative integral of e to the 2t over t dt. How do you integrate this? So that's the next big question. Any ideas, guys? No, you're right. I'm missing that. Oh, sorry, guys. Uh, sorry for making so many mistakes today. Sorry. Oh, okay, let's rewrite that. So we have negative integral of, thank you. That was a really good catch. Uh, okay, thank you so much. So g of t is t to the negative 2t times e to the negative 2t. That's g of t. And then y2 is e to the negative 2t. All over the Wronskian, that's e to the negative 4t. Yep. Thank you. Another mistake for today. So today is the day I make a lot of mistakes. So, yeah. Yeah. Oh, thank you. Yeah, it shouldn't happen, right? So, yeah. But yeah, sometimes we just let it go. But then we pick up. Okay, so how do we integrate this? Oh, this is nice. This is just negative 1 over t dt. Oh, that's heaven. Isn't that nice? So after making a lot of mistakes, I actually got something nice out of it. So thank you, all of you, for Shuman and I think that was Sadia. Yeah, it looks nice. So this is just negative ln of t in absolute value plus c1. Okay, so we have an expression for u. Now let's find v. So v is equal to the integral of g times y1 over the Wronskian dt. So g is t to the negative 2 times e to the negative 2t times y1. y1 is e to the negative 2t all over the Wronskian, that's e to the negative 4t dt. And this is also nice. We get this is equal to the integral of t to the negative 2 dt, and that integrates to negative 1 over t plus c2. So again, double check my work because today is the day I'm going to make a lot of mistakes somehow. I think, okay, thank you. Thank you. Keep checking on me. Alright, so we're almost ready to write out our final solution to this. So our general solution, it's going to be y equals u times y1 plus v times y2. So y is equal to u, that's negative ln of t in absolute value plus c1 times y1, that's e to the negative 2t, plus v, that's negative 1 over t plus c2 times y2, that's t e to the negative 2t. And then we just expand this and collect our terms, homogeneous and particular solution. So c1 e to the negative 2t plus c2 t e to the negative 2t plus, no, let's put minus. So we have negative ln of t times e to the negative 2t, that's the first one. And then the last one we have negative e to the negative 2t. Now we can make this solution look better if you notice that this one and this one, they're exact same solution. It's just multiplied by different constant. So I can just put it together and make it one term instead of two. So we simplify it to y equals a big C1 times e to the negative 2t plus C2t e to the negative 2t minus ln of t times e to the negative 2t. So that's our general solution. And from here we can pick up our homogeneous and particular solution. So any questions on this? And sorry, I screwed up so many times with the integration, so try not to do that. So here we have, yep. Oh, right. So what I did was I joined them. So we have C1 e to the negative 2t minus e to the negative 2t. I can factor e to the negative 2t, and you have C1 minus 1. This is just another constant, right? So just call it a constant C1. Okay, yeah. All right, so there you have another solution to second order non-homogeneous, right? So any questions, guys? All right, so let me just write down some identities that you should start recalling at this point. I think they're going to be useful for you when you are using this method, and maybe for future reference as well. So here are some identities. To know. So one, you should know the double angle identities. So we have sine 2 theta is to sine theta cosine theta. And another double angle identity we see often is cosine 2 theta. And this I'm just going to rewrite it as cosine squared theta minus sine squared theta. And really, if you remember the Pythagorean's identity, sine squared theta plus cosine squared theta equals 1, you can derive the other two versions of this identity. So there's two more you can fill in. And then you should also know half angle formulas. So we have sine square theta. We have 1/2, 1 minus cosine 2 theta. And then also cosine square theta, 1/2 times 1 plus cosine 2 theta. Okay, these are some useful identities you might encounter when you're doing integration for this method. All right. Okay, so any questions before we move on? Well, tangent, you can always rewrite as sine over cosine. So I wouldn't memorize it. All right. Okay, so that's the end of 3.6. So we're moving on to the next section, which is 3.7 and 3.8. So I like to do 3.7 and 8 together because it's the same concept, except 3.7 is homogeneous equations and 3.8 is non-homogeneous. So that's the only difference between the two sections. Okay, so 3.7 is labeled modeling with second order. So we learn how to solve these equations. Now let's do an application to them and we see how this is useful in some physics application, or maybe in chemistry. I don't know if you guys saw it in chemistry or not, but I didn't see it when I took it, which was a long time ago. Probably a long time ago, not too long time ago. But yeah, so modeling with second order, we will be modeling specifically spring mass. Spring mass problems. Okay, so this is 3.7 and 3.8. So when we studied first order, we did modeling with first order, and we were able to do initial value problem for tank problem, measuring the amount of salt in the tank, right? And then we also did compound interest. So that was for first order. Now for second order, we're going to be talking about spring mass. So here's an illustration before I give you the formula. So suppose you have, well, before I start, have you guys seen this somewhere in your physics course? Maybe? Yeah, right. So it's you probably have seen it different ways of solving these spring mass problems, but we're going to be using differential equations to describe the motion of the spring mass. But of course, there are other approaches to it. So let's look at this way, right? So here's an illustration. So suppose you have a spring. So I'm going to do my best to draw this. So here's a spring, a hanging spring. It has its own natural length. So I'm going to call this little l. So little l will represent, so little l is the natural length. Of the spring. Okay. And now what are we going to do? We're going to attach a mass to the spring. Okay. So here's another picture. So once you attach a mass to the spring, it's going to stretch some distance. So let's draw that. So here's the mass. So from the natural length, this was the natural length, it stretched some distance of L. So this is big L. So from there to here, we rewrite big L is the stretched. So let's so that's the length spring is stretched. Okay, so we have a system where we take a spring, a hanging spring, and attach a mass to it, and it stretches at some distance, big L. Now, so this is what the mass is. Okay, and now at this position right here, once you attach the mass, it's at equilibrium position. So this is what we call the equilibrium position. And now from this equilibrium position, you can compress the mass upward or you can pull it down. Okay, so and then you let it run. So that's the differential equation we're working with. We want to use the equation of the Newton's law that says sum of all forces working on a system is equal to mass times acceleration. So that's the equation we're going to use to find the differential equation for this particular motion. Okay, so that's where we're headed. So once you're at the equilibrium position, so let's call this equilibrium position, there is a force acting downward and there is also a force acting upward, right? So a force that's pulling the mass down is the for the gravitational force. So I'm going to call that F sub G, okay? And the force that's trying to pull it up is the spring force. So we're going to call it F sub S. So we have gravitational force acting on the spring. So that's Fg. And we also have F sub S, that's the spring force acting on this system. Okay, now we are going to consider downward to be the positive direction. So if you're pulling it down, that's positive, and upward, it's going to be considered negative direction. Okay, so that's also important. Now let's give some notation to this system. Okay, now the system you're looking at right here, it's in free oscillation, meaning we only have a spring and a mass, and you're just pulling the mass down or compressing it upward, and you let it run and describe that motion. So that's a free oscillation, meaning there is no damping involved in the system. If there is damping involved, then we have a damping force. So we're going to denote F sub D if there is any damping force in the system. Okay, so these are some of the forces acting on this particular system. Now let's derive some formula. Before I do that, do you guys know what is the gravitational constant equal to? Do you remember that from physics? So 9.8 meter per second square, or we could be using 32 feet per second square. Okay, so that's also important to remember what is the gravitational force. So we're using the Newton's law that says sum of all forces is equal to mass times acceleration. Okay, so we have the gravitational force, we have spring force and damping force, and sometime you'll be given a system which is involving section 3.8 that there will be an external force acting on the system. So we have a notation for that, G of T, which will represent external force. And this will be given to you usually in the problem. Okay, so now let's derive the formula. So we have sum of all the forces times mass times acceleration. So if I introduce some notation, let's use U of T. Let's call this to be the position function. If U represent the position function, that means U prime, it's going to represent the velocity function, right? And if I differentiate the velocity function, I have the acceleration function. So U double prime of T is going to represent the acceleration. So these are the notation we're going to be using instead of A, which represent acceleration. So I'm going to rewrite this equation I have. So we have sum of all the forces is equal to mass times acceleration. Well, acceleration is the second derivative of the position function, so this will be U double prime. Okay, so now what are the forces acting on this system that we're looking at from the equilibrium position? We have the spring force pulling it upward, and we also have the damping force that's also acting against the gravitational force, so it's also negative. Okay, so what are the forces we have? So we have spring force, which is negative, and then we have the damping force that's also negative. Okay, and sometime you'll be added an external force to the system, so we have a G of T that's also acting on the system equals to mass times acceleration. So that's the formula we have. And I'm just going to rearrange everything so it looks better. So we have M times U double prime plus the damping force plus the spring force is equal to G of T. So this is the differential equation we're working with. Well, now we have to define what is the damping force and what is the spring force, right? If you remember from calculus, spring force is the force required to displace the mass from its equilibrium position, right? So this force is negative K times U, because it's K is the spring constant And Fs, which we're calling a spring force, it is a force that is required to displace the mass right here from its equilibrium position. So that's Fs. So we have, this is U times K times U. So that's a spring force. Now what about the damping force? So let's define what is damping force. Damping force, it's going to be the resistant force over velocity. So we're going to define damping force as resistant force over velocity. So usually it'll be given to you in the problem, but if it's not given, then that will be a way you can find the damping force. So this is going to be gamma, which is the constant, the damping constant, times U prime. So gamma is the damping constant. Okay, so by plugging this into our equation, we have gamma times U prime, and we have M times U double prime. Everything equals to G of t. So we have the differential equation that describes the motion of the mass. So this equation describes the motion of the mass. Okay. Now we also have to impose initial conditions. So we're going to impose U sub 0, which will be the initial position of the mass. And then we're going to inscribe U prime of 0, which is the initial velocity of the mass. So there we have an initial value problem. Okay, now the question is, how do you compute these coefficients? So m is the mass, right? So if you recall again from Newton's law, we have, so how do we find these constants? How to find m, gamma, and k. So k is the spring constant, gamma is the damping constant, and m is the mass. Well, you should remember the force is mass times acceleration, right? Because we're applying a mass to a spring, there is a weight force that acting on the system. So we have the weight is equal to mass times the gravity. So that means you can find m is equal to the weight over g. So that's the way we're going to figure out what is the value for m. And what about the spring constant, k? Well, if you again recall from calculus, the force is equal to k times L, where k is the spring constant and L is the length it is stretched. So this would be the way we can find k. So k is going to be W over L. So that will be the way we can find the value for k. And what about gamma? So that I gave it to you right here. Gamma is the damping constant, which is resistant force over velocity. Okay, so we have gamma defined as resistant force over velocity. Okay, so that's how we will determine the value for gamma. Alright, so there we have it. We have a setup for a spring mass. Let me know if you guys have any questions. So I'm going to do one more illustration before we do an example, but I'm going to pause that for next class. So, any questions for today's lesson? Right? How do you guys feel? Okay, coming along. All right, that's good. So we are done here for today. Let me know if you guys have any questions. I have office hours 8 to 9. If you want to stop by, say hello, please do. I'll be here if you need any help. So the quiz will be up to section 3.6. I'm not going to put 3.7 and 8 because I haven't done any examples on that. So this is just for your reference. There's no spring problem on the quiz, so just 3.6 and 3.5. Okay.